Welcome. This is Dr. Morton, and this is the lecture um, for state machine. Okay, so here are the slides, and we'll just go ahead and start. Again, these are the objectives we already covered. We already covered this, and here's our state graph. Now, what I want to point out here, let's take a minute and look at this. First, we want to ask, our target are 0, 1, 0 and 1, 1, 0, okay? How many states do we have? Well, we already said this, but we have one state here. Note the dashed lines are our state blocks. This is our state box, but the dashed lines are our state block. Here's S1. We have, and again, every block must have one state box and only one. It could have decision boxes, and if this were a mealy, it could have some conditional output boxes. But since this is a more, there will be no conditional output boxes because those are always mealy outputs. But it does have more outputs, and they're always associated with the state box. So here you see Z is associated with the S3 state box, and when it appears, that means it's 1. When you don't see it, then it's 0. All right, and this little 0 down here is a mistake. Just ignore that. It's a typo. All right, so how many states? Well, 1, 2, 3, 4. 4 state blocks, 4 state boxes, 1 in each block, and 4 states. All right. Okay, how many inputs do we have? Well, if the basic design then for this problem, and let me just do this. Let's see. I wanted to switch this. Okay. Okay, we'll write on paper here. So remember, this problem is basically our standard setup, right? We have our network here. We have one input X. We have a clock, an edge clock. It could be rising or falling. I don't have a bubble, so we'll assume it's rising edge. And we have an output, Z. So one input X, one output Z, and here's our network. Well, here's our, sorry, not our network. Here's our state machine. And it has 4 states. It has 2 flip-flops, because with 4 states you got to have 2 flip-flops. And so what we're going to do is we're going to work those. Okay, so in this case we have one input, one output. When there's no decision box, what does it mean? Well, it means there's only one path out. And in this case, from S0, we always go to S1 because whether we get a 1 or a 0, we still have the possibility of the next of the first item in our target sequence. We have no essentially no decision box in S3 because although that is a target, but our next value coming in is always going to take us to S1 because either way it's the first value in a possible next 3 value sequence, right? All right, so that's why when there's no decision box, it means that on X equals 0, X equals 1, we go to the same place. Okay, what do the dashed lines mean? They enclose each block. That's a block, that's a block, that's a block, that's a block. All right. Okay, so let's now see how we can assign our flip-flop encoding. We'll just do state binary. So 2 flip-flops, A and B. So this will be A equals 0, B equals 0, or A prime, B prime. This is A prime, B, or 0, 1. This is 1, 0, or AB prime. And this is 1, 1, AB. Now that we've assigned these, we can actually immediately write the equations for the DA input, the DB input, and the Z output. And here they are. But let me show you how we do that. So I'm going to... All right, so here's our example. Now I'm going to write in, so this is A prime, B prime. This is A prime, B. This is A, B prime, and A, B. Those are our flip-flop encodings. So once we have this, it's really easy to write the states. Notice I'll also write in this node means we have nothing. This one means we have the first item, and I'll just call it X because it could be a 1 or a 0. This means we have X1 because it could be a 1 or a 0. And this means we have X10. That's our target. All right. So how do we develop our DA input? Well, so our DA input equals basically the equation for every path into every node where A equals 1. Well, A equals, it's A prime here, so that's a 0, so we don't have to worry about S0. A prime is there, so we don't have to worry about S1. But A is 1 for S2, and A is 1 for S3. So how many paths do we have into S2? Sorry, S2. How many paths into S2? Well, just 1, and it comes from S1. So we write that S1 would be A prime B, right, because of that. And when X is 1, so it's A prime B, X. And then we also have the path into S3. And the path into S3 comes from S2 when X is 0. So that's going to be A, B prime, X prime. A, B prime, so that's state S2. And X prime, because when X is 0, we go to S3. When X is 1, then we would go back up to S1. All right, so that's the DA input. The DB input, and we can't simplify that. It's as simple as it gets, I think. Okay, so now the DB input, we want every path where B equals a 1. Well, here it's B prime, so we ignore S0. Here, B is a 1 in S1, so we have to every path in S1. How many paths go into S1? Well, one path comes from S0, right here, but another path comes from S3 all the way around here. Notice they both go in at the same single entry point, but they're 2 exit points. So they come in at this same entry point. So the first one then is going to be from S0, which is A prime B prime, and there's no X involved, so it's just A prime B prime, because it goes there whether X is 1 or 0. All right, and then the second path also comes from comes from S3, but it only comes when it doesn't depend on X either, so we just write A, B, because that's what S3 is. And now, what else? Well, S2, the B is a 0, so we're not going to worry about that. But in S3, we do have a B is 1, so we have to account for every path into S3. There's only one path in. It comes from S2, and it comes from S2 when X is 0. So S2 is A, B prime, and X prime, because X is 0 when it comes in. So now we have this, and we can't simplify either one of these, I don't think. So we're basically done. And now for our Z output, because the Z is a more output, it only depends on the state. So where do you see Z? The only place you see Z is right there, and that's where Z equals 1. Everywhere else you don't see it, it's 0. And so Z only depends on the state, doesn't depend on X. So Z just equals A, B. Because when A is 1 and B is 1, we're in a state S3, and that means we've detected a target. So Z equals AB. And now we have solved the problem. Didn't use a K-map, didn't use a state table, but we do have to, we are assuming that we're using D flip-flops. So we don't have to write those additional columns. If we're using JKs, then this is going to be a problem. Now we're going to have to basically do the other method, or adds a lot of additional work to this. But if we just use Ds, this works fine. And so that's our solution. And notice we didn't have to do state table, transition table, K-maps, or any of that, and we can just write our solution. Okay, so now that's a good introduction. The only thing we didn't include in that introduction is how do we handle Mealy outputs. And so the next thing we want to do is to look at that. Okay, so let's do that. So same problem with the Mealy. All right, so again, our targets are 0, 1, 0, or 1, 1, 0. And so that means in this case, we're going to start and in S0, and we'll code it A prime, B prime. If we, doesn't depend on X, regardless of whether we get a 1 or 0, we're going to S1, and we have the first item. Now in S1, if we get a 1, we're going to S2, because now we have the first two items in our sequence, 0, 1, or 1, 1. But if we get a 0, we're going back to S1. And notice we come into this same link path entrance. Now that we're in S2, if we get a 0, then that would be 0, 1, 0, or 1, 1, 0. Either one would be a target. So this is our conditional output box. So if X is 0, we go through the Z, which means Z equals 1, and we take this link path and we go all the way back into S0, where we'll be ready for the next input. If on the other hand, the new X is a 1, now we don't have anything. So we're back to, we didn't get our target, so now we reset to S0. And notice these two paths go back in the same place. But when we do the analysis, there actually would be, 1, 2, and 3 paths into S0. But you could also just model it as a path from S2 that doesn't depend on X. But in one case, you do have the conditional output Z. All right, so for the A flip-flop input, it doesn't matter. But for the Z output, then we do have to keep that in mind. All right, so let's write the equations then. The one other consideration here is that because we have only used 3 of our possible 4 states with 2 flip-flops, we do have a don't care state. And the don't care state would be AB or ABX prime plus ABX. So you could combine these and make AB. So any of these would be legal don't cares that we could choose however we want because they'll never occur. All right. Notice how the Mealy output is in this conditional output box. It is not in our state box. We have no outputs in our state box because this problem doesn't have a more output. It only has a Mealy. And in our more output, so you can see the Mealy output here. In the more output, notice there's only an output in S3. The Z is 0 in all these, and there's no conditional outputs because there's no Mealy outputs in this more problem. Now you could have both, and you will see that. And with SM charts, it's easy to do both. If you have Mealys, then you just have a conditional output box. If you have mores, then you have outputs associated with the blocks, with the state block. And not only that, or with the state box rather, not only that, but you can have the same output as a more and as a Mealy mixed into the same problem. But sometimes they're different, sometimes they could be the same. All right, so let's solve this problem then. Okay, so now we're going to solve these problems. Let me turn over here to the paper. And so you can see, so we have our 1, 2, 3 state, we have our 3 blocks with a state box in each one. 2 of them have conditional boxes, and 1 of them has a conditional output box, which is our Mealy output Z. All right, so all we have to do is we have to account for all the paths into all the boxes where A is 1 for our D sub A. So we switch this in like this. Okay, so D sub A is going to be equal to all the paths where A is 1. Well, where is A is 1? Only in S2. So we only have to account for this one path into S2. So dA is going to be A prime BX. A prime BX. And dB is going to be all paths in where B is 1. Well, B is only 1 in S1. So we only have to account for this one path from S0 into S1. There's no X involved, and so that's just going to be A prime B prime. Now, notice that we do have a small advantage in this case because we do have these don't cares. So let me switch back to here. So notice we can use AB prime X, ABX prime, ABX, or just AB by itself. All these are don't care options that we have to simplify our expression. And so let's do that. So if we do that, let's see if any of those are helpful. So we'll write these down. Okay, so we can use don't care, AB, R, A, B, X, R, A, B, X prime. Well, let's see. ABX would be useful. We can combine it with this one, and that will just give us BX. And this one's about what it can be. Now, what about our output Z? Well, because this is a Mealy output, it depends not just on our state, which in this case is S2, and that would be A, B prime, but it also depends on the next X. In this case, it would be when X is equal to 0, and therefore it's X prime. Now, can we help this? ABX prime and ABX? Yes. We can use this one, and we can say plus ABX prime. And that would then give us, that's equal to AX prime. So that's our dA, that's our dB, and this is our Mealy output Z, AX prime. Again, pretty simple, right? Amazing that we can solve the problem so quickly without having to go through all the issues of state graph, state table, flip-flop state assignment. We still have to do flip-flop state assignment, but we don't have to do the transition table. We don't have to do the K-maps. We can still use our don't cares. We just have to use them algebraically, and then we can write our equations, and then boom, we have our solution. So that's pretty amazing. Yeah, pretty amazing. So if we go back to the book, you'll see that here's a new problem. Now we haven't really described it, but notice that we have we were given the SM chart for an unidentified problem with several inputs. Notice it has 3 inputs, x0, x1, x2, and then we have 2 Mealy outputs, or 3 Mealy outputs, ZA, ZB, ZC, and then we have more outputs, Z0, Z1, and Z2. So we have 3 Moores, 3 Mealys, and 3 inputs. Pretty complicated. We'd be using, and we have what, 1, 2, 3, 4 states. So we'd have 2 flip-flops, 3 inputs. We'd have 5 independent variables. So we're already into 5 variable K-maps. So it would be a bit of a pain to solve this with K-maps. So if you notice, we've already done flip-flop state assignment. We just used straight binary, A prime, B prime, A prime, B, AB prime, and AB. All right. So now let's go back to the slides. And here we are. So the first thing, how do we solve for? So we have 2 flip-flops because we have 4 states. So we have an A and a B flip-flop, and then we have 6 outputs. Okay. So let's first do our our outputs because they're actually a little simpler. And so let's do them. I guess we're going to do we'll do the more outputs first because they're easy. So that would be ZA, ZB, and ZC. So if you look at this, let's do ZA first. So where does ZA appear? Well, it appears in that state S0, and it appears in state S2. Okay. So then ZA would be equal to A prime B prime plus AB prime, and that easily simplifies to B prime. All right. What about ZB? ZB only appears once, and it's in S1, so it's A prime B. ZC only appears once down here in ZC, so it's just AB. What about our Mealy outputs? Well, Z0 appears twice, okay, once in S1, A prime B and X1 equals 1. So Z0 is A prime B X1 plus, it appears here in, let's see, where's our Z0? Yeah, it appears in S3, and it doesn't depend on X here, so it's just AB. And that simplifies then to BX1 plus AB, and I think that's because of our don't cares. No, we don't have any don't cares here. Oh, that's using the, because we have an A prime B, we have an AB and an A prime B here, you can drop the A prime. Okay, and then now we have Z1. Z1 appears here, and that's it. So so it doesn't appear twice. So we just have to account for S2 where where X2 equals 1. So that would be A B prime X2. So Z2 is A B prime X2. Sorry, I got ahead of myself. Z1 then would be A B prime X2. And then Z2 is A B prime X2 prime, because it's where X2 is 0. A B prime X2 prime. So now we've described all 6 outputs, the 3 Moores and the 3 Mealys. And now we just have to do the ZA input and the ZB, or the DA input rather, and the DB. So DA, so where is A equal to 1? A is equal to 1 in S2 and S3. So we need to account for all paths into S2 and all paths into S3. So how many paths are there into S3? Well, there's a path that comes from there. Well, let's do S2 first. There's a path that comes from S1 when X equals 1. Okay, so that would be A prime B X1. There's another path that comes from S2 itself. Now, I didn't mention this earlier, but I didn't want to confuse things. There's one other rule I didn't tell you about, and that is you're not allowed to have a path inside your node go back and re-enter without going out of the state block and back into the state block through the one and only one entry point. Okay, so when X2 equals 1, we have an output Z1 equals 1, and we go out and then back in. So in this case, we plus AB prime X2, AB prime X2, because that's the path that comes back into S2. So that's 2 paths into S2 accounted for, and now we have to account for 2 paths into S3. One comes from S0, so that would be A prime B prime X0 prime, and the other one, A B prime X0 prime, and the other one comes from S2, so that would be A B prime when X2 is prime. So X2, right, A B prime X2 prime. So now, let's see, I'm getting myself confused. A B prime X2, right, sorry, A B prime X2 prime, this term. So these 2 terms are for S2, 2 paths in. These 2 terms are for the 2 paths into S3. A prime B prime X0 prime, that's coming from here, and AB prime X2 prime, that's coming from here. All right, and so that's our 4, and we can simplify that down to this. All right, and then DB, we have to account for S1, all the paths into S1, and all the paths into S3. In S2, B prime is a 0, and S0, both A prime and B prime are zeros. All right, so we account for the paths into S1. 1 comes from S0, A prime, B prime, X0. A prime, B prime, X0. 1 comes from S3, which is going to be A, B, and it doesn't depend on X. And then we have the paths into S2. 1 comes from S1. No, sorry, into S3. And that's going to be the same as the ones up here. A prime, B prime, X0 prime. A prime, B prime, X0 prime. And AB prime, X2 prime. AB prime, X2 prime. And now we can simplify it, and we get A prime, B prime plus AB prime, X2 prime. And so those are our final equations. Simplifying them with switching algebra. And you can see, even though this is a fairly complex problem, it's a whole lot easier to do it using the state machine chart than it would have been the way we just learned. Okay. All right. So what have we learned? Well, so we've kind of done the state machine chart now with some simple problems, both a Moore and a Mealy, and then now with a more complicated problem with 6 outputs and 3 inputs, and it was easy, right? No big problem. So if you get confused, go back and just review these things. Sorry, I guess you couldn't see that. Let me move my picture. Maybe turn me off. I'll put this back over here, and I'll turn me off so you can. No, that didn't do it. Oh, I see. Got it. Let me do this. Me video. Yeah, here. Okay. Now, all right. Now you can see the other terms here in case you missed them earlier. You can see the other terms here. All right. Great. Okay. Okay. So I wanted to talk about some additional features of state machine charts that make them sort of useful. It doesn't change, your outcome, your solutions, or anything. But notice here, we have one chart that looks like this. This is just a single block. And then we have another single block that looks like this. But they're entirely equivalent. Now, at first brush, this looks impossible. But remember, I said you can have more than one link path active at the same time as long as they exit the same point. So in this case, you could have, let's say, you have a parallel way to look at it and a serial way to look at it. So if say x0 is a 1 and x1 is a 1 and x2 is a 0, then let's see what you'd have. That may be a little confusing, but notice, let's see, well, let's say they're all 1. Okay, that's easier to remember. So we start in S0, and x0 is a 1. Okay, so you're going to take this path. So you will not have a Mealy output z0 equals 1. It'll be 0 because there's no conditional output box on that path. And then it exits here. Then you have a path active here, which in this case, x1 is 1. So we will have z1 equals 1, and it exits. And then for x2, we would also have, if it's, again, all three, we're saying all three happen to be 1, then x2 is a 1. So now we have also a z2 Mealy output. So now we have z0 equals 0, z1 equals 1, z2 equals 1. But they all exit the same point. Now look at the serial approach here. So x1, so we skip the z0. We go here, we go this path, and we get z1, and then we go, oh, you know what? They're not the same. I switched the 0 and 1 here. I should fix that. Didn't realize they're an error. So in this case, this should be a 1. We should go z2, just like we did here. So they're close to the same, but actually there's a mistake here. Okay, well anyway, so that pretty well covers how you can use these charts to visualize your problem in different ways. And for that reason, these charts are really, I think, pretty valuable and very helpful in giving you a better tool or another tool to solve state machines. Now you can see, if we went back to our traffic problem, how easy this would be, and maybe in class on Wednesday I'll work that out for you. All right, so I'm going to quit. It's been 30 minutes, and hopefully you already did enjoy the Eclipse, or you will enjoy the Eclipse, and we'll see you on Wednesday.